Hello, it's Mr. Adler. Got another flipped lesson for you today. Today's lesson is on motion formulas. These motion formulas can be found on the back, page 6 of the physics reference table. They look like this. And the reason why I'm doing this lesson is because a lot of times students look at all these formulas and get overwhelmed. There's so many different formulas with lots of different variables, and that can make you a little nervous about trying to solve problems that you're going to be given. Want to make it a little bit easier with some strategies and some hints. First of all, looks like we're looking at 5 formulas, but we're really not. I don't want to get too tricky, but if we take a look at one of these formulas, this formula for acceleration, it says that acceleration is the change in velocity divided by time. Really, to find the change in an object's velocity, you need to know the difference between their final and their initial velocity. So if we rewrite this formula, it starts to look like one of our other formulas. If we move some stuff around, let's cross multiply, we get A times T equals VF minus VI. And then we add VI to both sides, we end up getting a very familiar formula, the one that was right next to it. That's the formula right here. It's switched around on the equal sign, but it's the same thing. So really, we're only looking at 4 formulas. Even that can be overwhelming. When you have 4 formulas, a dozen word problems to solve. So I want to give you some strategies. First, after we've reduced some of these formulas, let's talk about how many variables we're looking at. As I start writing out some of these variables, and make a little list, I guess, of variables. We've got average velocity, distance, time. That's from the first formula. Then we go to the next formula, acceleration, and final velocity and initial velocity. After that, all the other formulas have those same variables in it. So suddenly, 5 different formulas is really only 4 formulas, and all those different variables, it's really only 6 variables. It's more than 1, but it's not 20. It's not a million, stuff like that. So that's the first thing to remember. When you're looking at all this stuff, there's a lot of repetition in the formulas, both the actual formula and the variables. I guess that's kind of the same thing. Here's my second strategy to remember. The variable that's all by itself in the formula, let's use this one again. That doesn't have to be the variable that you're solving for. This formula doesn't mean you can only solve for VF. If you knew VF, you could solve for something else. It's the same for all the other formulas. You don't have to just solve for the variable that's all by itself. And we're going to practice this. My last strategy, that's really not my last strategy, but I'll say that for now. Once you've sort of gotten over some of the nerves and it's time to pick out the right formula, you're going to pick out the one that's right for the problem. Here's the big idea. If you can fill in all the variables, if you know all the variables except for the one that you're trying to solve for, that's the formula that's going to work for you. That's the way it's always been. I'm not saying anything new here. That's the way math and science have always solved for problems. But a reminder is pretty helpful. You figure it out by doing something that I know a lot of students don't like to do. You have to write out the variables off to the side of the problem. Some people just want to read a problem, get overwhelmed, and go, I don't know what to do. Getting a little too old for that. Write out the variables you know and what you're trying to look for, and then match those up with the formulas and find the formula that just has those variables that you know plus the one that you're looking for. While we're doing this, it's also important to remember that we want to remember our units. In the Regents class, units are a big deal, especially at the end of the year. It's a lot to add to in this story, but we're going to try. For sure, you want to write down the variables when you're substituting into the formula the first time, so that you have the right correct variables, the right correct units, at the end of the problem. But also, as you practice this and you start to look at some of the units, they're going to help you figure out what your final answer is and how it helps. that might be something that you need to practice in class with a teacher nearby. Let's see how we can do. Let's get to some practice problems. Here's one. I'll read it to you. Maybe if you're taking notes, which is always a good idea, you want to write this down in your notebook. A bobsled has a constant acceleration of 2 meters per second. If it starts at rest, how fast is it going after 5 seconds? Very typical problem that we might have. Let's start by writing down what we know. Okay. Bunch of things on there. We know it has an acceleration of 2.0 meters per second squared. It starts at rest. It's not a number, okay? But those words mean the initial velocity is 0 meters per second. How fast is it going after 5 seconds? The 5 seconds is the time. How fast is it going is what we're trying to figure out. That's a final velocity. That's our unknown. So we start looking at some of these formulas. Which one might work for us? It looks like this one right here. That's what we're looking for, final velocity. And it's nice also because it's the variable that's all by itself. So now we start plugging in our numbers. We're looking for final velocity. We know the initial velocity is 0 meters per second. The acceleration is 2 meters per second squared. And we multiply that by the time of 5 seconds. That's not that crazy. X equals 0 plus 10. And if you look at the units, we've got meters per second here. I know it's 0, but we're adding it to this stuff right here. And this stuff right here, meters per second squared times seconds. The seconds of time cancels out one of the seconds in the acceleration, and you're left with meters per second. We can add meters per second to meters per second, and that's why our answer is in meters per second. Hopefully, that didn't look like too much magic. Let's try some more. Now we have some more information, so I'm going to use some of these numbers again. Here's our formula, and here's our second problem. How far has that bobsled traveled in 5 seconds? We can use a lot of the information from the last question. Acceleration is still the same. The initial velocity is the same. The time is the same. But now we even have one more bit of information. We know the final velocity is 10 meters per second, which is nice. We want to know what the distance is. It's not going to be the first question. It's not going to be the first formula, the second formula, or the third formula. They don't have distance in the problem, in the formula. So we can't use those. So it's got to be one of the last two. And it turns out that in the last two formulas, we know everything but D for both of them. So sometimes it even works out that you have a couple of choices for formulas. Let's try both. Let's start with this formula. It makes a nice way to double check to see if we know what we're doing here. Okay? We're trying to find D. We know that our initial velocity was 0 meters per second multiplied by the 5 seconds of travel time, plus 1/2, the acceleration was 2 meters per second squared for 5 seconds. And we square the time, only the time. 0 times 5, that's nice. 5 squared is 25, times 2, that's 50. You cut it in half, 25. Now you might not see this from the units, but we've got 2 meters per second squared times the 5 seconds, which is squared. So that means the units for time became seconds squared. That cancels out seconds squared in the numerator from seconds squared in the denominator, and all you're left with is meters. Hopefully that doesn't sound too tricky. Hopefully that makes a lot of sense, because distance should be measured by meters. So 25 meters is our answer. We are lucky enough that we could use the other formula to double check. So let's do that. I'm going to get rid of all this. And if I got rid of it too fast, don't forget, you can always hit the pause button and go back and try it again. Here's the other formula. VF squared equals vi squared plus 2ad. For me, it almost looks like a smaller, simpler formula. So maybe for me, that's the one that I would try first. It doesn't matter. If we're doing things correctly, we should get the same answer. If we don't, we should tell ourselves, I think I did something wrong somewhere, and we have to go back. VF, we know, is 10 meters per second. We have to square that. The initial velocity was 0 meters per second. We have to square that. That's not going to be hard math. 2 times an acceleration of 2 meters per second squared. And we know from the last problem, oh, we're trying to find distance, excuse me. That's the one thing we don't know. Always tell yourself, if you fill in every variable with a number, you've either done it wrong or you're using the wrong formula. You're trying to solve something. There needs to be one unknown in the problem. 10 squared, that's 100. 0 squared, I'm going to ignore that because it's 0. So the only thing I have on the right side of my equal sign is 2 times 2 times d. I divide both sides by 4 to get d all by itself. D equals 25. And it should be meters. Okay? This is a little tricky, but if you look on the left-hand side, meters per second, and that's all squared. So that's kind of like, I'll do it off here, meters squared per second squared. On this side, we've got meters per second squared times whatever d is. Well, to make both sides be equal, the d has to be a meter so that you have the same amount of units, the same units on both sides. If that doesn't make sense right away, that's something that comes with practice. That's pretty high level stuff right there. Okay? But that's how we know that the units should be meters. Now, of course, we also know distance ought to be measured in meters in our class. Right? We have more than one way to do that problem. Sometimes that's really nice. Okay? Last question, because there's a couple of other ideas we got to think about. Here's our formulas again. This might not seem like too much of a tricky problem, but there's a couple things we need to think about, a couple of assumptions to make. Here's the question. A stone is dropped from the top of a school. What is its velocity 2 seconds after it's released? Now, it's kind of a weird question because it only looks like there's one variable in there. But we know a few things, okay? More than just time is 2 seconds. It's dropped from the top of the school. So the moment that it's dropped, what's its initial velocity? As soon as you open your hand, it starts to fall. But that initial minuscule second where you let go, it wasn't moving. That's an important thing to remember. It's not saying you threw it. It's just saying you let go of it. So for the instant that your hand finally let go of it, it was moving 0 meters per second. Right after that, it started to move. How come? Because of gravity. Maybe you remember, maybe you've heard the story of Leonardo da Vinci or Galileo on the top of the Leaning Tower of Pisa, dropping a large cannonball and a small cannonball, and they fell at the same rate. That rate, that acceleration due to gravity, if you don't know, you can always find it on the front page of the reference table. That acceleration, which we call the acceleration due to gravity, is 9.8 meters per second squared. Whenever something is in free fall above planet Earth, it falls at an acceleration of 9.8 meters per second. So that's another assumption you can make when you know you've got a problem involving free fall. Okay? And that's what this one is. We're trying to figure out what its velocity is after the 2 seconds. That's VF. Now, I didn't pick this one because, oh, we're going to use this formula again. I picked this question so that we could talk about initial velocity being 0, acceleration due to gravity being 9.8. And so now we can hopefully do this problem a little quicker. We're trying to find the final velocity. We know it started at 0 meters per second. Gravity is pulling on it 9.8 meters per second squared for 2 seconds. Not too much math to do here. 19.6 is 9.8 times 2. And again, meters per second squared times seconds leaves you with meters per second, which is a very common, which is the typical velocity. The truth is, in the absence of air resistance, all objects that fall above Earth for 2 seconds are going to do that speed. Of course, in the real world, there's air resistance. So it's not always that simple, but this is how we start doing physics. Okay, I think we have time for one more problem. And this time I really mean it. It's one more problem. Let's get to it quickly. There's the formulas. There's a question. This one's a little different also. It's saying if the stone had been thrown into the air with a velocity of 30 meters per second, how long would it travel upwards? I think you know that when you throw an object into the air, it slows down. Gravity is pulling on it. Hey, you throw it up, but gravity is pulling it down. That's really important to remember. It's thrown into the air with a velocity of 30 meters per second. That's its initial velocity. We want to know how long it's going to travel upwards, which means it's eventually going to stop traveling upwards. So its final velocity will be brought to 0 meters per second after a certain time. That's what we're trying to find. And this is all due to gravity. Here's the important part. You let the initial velocity of 30 meters per second, positive 30, represent you throwing the stone upward. Which way is gravity trying to pull it? Downward. That's the opposite direction. So the acceleration due to gravity, that g, is still 9.8 meters per second. But in this case, since 30 meters per second represents the stone going up and gravity is pulling it the opposite way, we're going to make that 9.8 negative. That's super important. Gravity is slowing it down. That's what in physics terms we call negative acceleration. And for the last time, we're going to use this formula. It's not the only formula we use this lesson, but we used it a bunch so we could talk about several things. The object's eventually going to come to rest after it started at 30 meters per second. But it was slowed down because of gravity after how many seconds? So we start to reduce this problem. 30 plus negative 9.8 t. Don't get scared of the negative. Look, all your numbers are on one side of the equation. When we want to solve for t, let's bring t to the other side. So we add, because it's a plus negative 9.8, we add plus 9.8 t to both sides, and we get 9.8 t equals 30. Divide the 9.8 out. And the time that object would go up into the air before it stopped would be 3.06 seconds. I rounded it a little bit, but that's pretty good. Now remember, I could make this even tougher. How long would the stone be in the air total? Well, it's 3.06 seconds to stop going up. And thanks to gravity, it's going to be 3.06 seconds to come back down. So a question that asked you how long was it in the air? Do half the motion and double it. And you could figure that out. There's lots to figure out through practice. Okay? And that's why this lesson's pretty much over, so that you can then come into class and work on problems that are going to extend your knowledge a little bit with a teacher nearby to help you out. Hopefully this gets you on the road. Good luck.